Welcome to my topic, Circuits and Networks. I am Ravikant Malajoshula, and today we are going to deal with class 2 of single phase AC circuits. Particularly, we are going to see the behavior of the waves when they are going to apply to passive elements like resistor, inductors, and capacitors. How do they behave individually, and how they are going to behave when they are combined, whether in series or parallel arrangement. What we have seen from our previous classes is about the waves, that is, if two waves reach their maximum and zero values at the same time, they are said to be in phase, whereas the phase difference term is used to compare the phases of two sine waves. So this we have derived from our previous class. You can see there are two sine waves. One is in red color, one is in green color. The red wave is starting from 0 and it has reached to some time period. Then there is a green wave which is started before the 0. So this I am going to treat it as reference. So the green wave has started before the reference. Here you can see the representation of two other waveforms. One is in orange color and blue color. If I treat orange wave as a reference, the blue wave is going to start after some time. So how to understand this wave behavior? So if I'm treating the red wave and the orange wave as voltage wave VA, which is given by VA is equal to Vm sine omega t, then green wave I'm treating as VB, voltage wave VB, which is Vm sine omega t plus phi. Similarly, I'm treating the blue voltage as VC. VC is equal to Vm sine omega t minus phi. With these two waveforms, that is VB and VC, compared to the reference waveforms VA, we can state as voltage VB leads VA by angle phi. Similarly, voltage VC lags VA by phi. So these basics are very important to understand the behavior of a voltage wave, a current wave, a power wave in any electrical or electronics network. Hence, we are going to start with the application of sinusoidal voltage applied to resistor. In my later classes, we are going to see the same wave applied to inductor, capacitor, and later on the parallel or series combinations of the passive elements. So here you can see a source voltage is represented by V and it is delivering current I in resistor R. So what is this V, I and R? R is the passive resistive element. Current I, it is flowing because V is applied to a closed circuit which is having a load of resistance R. So here V is equal to Vm sin omega t is a reference value we have taken, where small v is treated as instantaneous value of voltage. Vm, it is treated as the maximum value of the voltage, and sin omega t because the time period it is varying from 0 to infinity. So that condition we are taking as omega t. So let us treat this instantaneous value of voltage as equation 1. We also know that according to Ohm's law, V is equal to IR. So whenever this voltage is applied to a resistor, the voltage developed across resistor will be given as V is equal to IR. With this, I am going to get the value of I is equal to V by R. What is V? V is the instantaneous value of the voltage applied to resistor. So when I have to obtain the instantaneous value of current, I am going to obtain like this: Vm by R sin omega t. Now I is equal to Vm by R sin omega t. This is known as the instantaneous value of current which is flowing in this resistor. So if at all I want to replace Vm by R according to Ohm's law, it becomes Im. Im is equal to the maximum value of the current which is associated with sin omega t. So the instantaneous value of current will be equivalent to Im sin omega t. So this I am treating as equation 2. Now V and I, we got the instantaneous values of voltage and current when they are applied across resistor. So applied voltage V, that is the instant value of voltage, and the phasor representation of I, you can see V is equal to Vm sin omega t, whereas I is equal to Im sin omega t, where Im is equal to Vm by R. So it is easily understood that the amplitude of the voltage, it is divided by the resistive element. That is why in phasor representation the I has less in magnitude compared to the input voltage, but both are acting in the same direction. So here V and I are said to be in phase. That is what we have seen from the first statement at the beginning of the slide. Now a standard RMS representation of voltage, Vrms is equal to Vm by root 2. If this is true, then it is also true that Vm by root 2 is equal to Im by root 2 R. So this is for easy reference. When we have to obtain the voltage across resistor, the voltage across resistor is equal to IR, where I will be the instantaneous value whose value will be equal to Im by root 2. So these are the basics that you need to understand in order to understand the behavior of sinusoidal input to any passive element. We have started with resistor, and the later stage we are going to deal with inductors and capacitors also. Now, in order to understand the behavior of the wave, you can see V and I are represented on the y-axis, and on the x-axis we have time period, and the value it is reaching from 0, pi and 2 pi. This is one time period, and you can see the value of voltage, it has reached to the maximum and it has gone to the 0, then negative maximum, and it has rested to 2 pi. Now V is the instantaneous value and I is the instantaneous value. It is also, you can see, operated in this form. So these values are nothing but the RMS values placed in the instantaneous graph. Okay. Now if this is true, let us calculate the instantaneous power. So P is equal to V into I. You can see the V and I in small letters or case sensitives are said to be in instantaneous representation. Substitute the value of instantaneous voltage, instantaneous current. So this is the values. Then I have taken Vm Im outside. So sine term becomes square times omega t. So this in trigonometric way I can represent it as 1 minus cos omega t by 2. So this becomes the instantaneous power. So you can see Vm Im multiplied with 1 by 2 becomes the constant power for the given waveform, minus Vm Im cos omega t by 2 becomes the, it becomes what? It becomes the varying value of waveform. The varying value because it has associated with cos omega t. So you have the constant power in combination with the rotating power. Then how to estimate the average value of power? The average value of power, it is starting from 0 to 2 pi. So 1 by 2 pi. So the total waveform we are selecting 0 to 2 pi. Vm 1 minus cos omega t dt, in fact d omega t by 2. So this integration we need to apply. So one will be the constant term and one will be the variable term. So constant term will be giving you the value as Vm Im by 2, whereas this variable term integration of cos is sine, and you have sine upper limit lower limit values as 2 pi and 0. So sine term with 0 value or multiplications of pi value will always give you the result as 0. So in fact the average power will be Vm Im by 2, or you can replace this Vm Im in terms of the instantaneous values as Vm by root 2, Im by root 2. In fact, these can be treated as the RMS values. So in fact, RMS value of power is equal to V into I. So this is how mathematically we can represent the waveform of a sine wave in terms of voltage and current. So these obvious things you have seen in your previous uh, intermediate or 10th class courses. So this is how it is obtained. Now how to understand this waveform behavior? So we are substituting the instantaneous values of voltage and current, and we have obtained the power curve. What is this power curve? We are going to see in this figure 3. That figure I am going to show you right now here. And by this above derivations, it is indicated that voltage source is delivering the constant power to the resistive load connected to it. So we have seen the value as Vm by 2. So that is the constant power which is delivered to the resistive load. So this is the waveform we have, and here we are adding another parameter, that is the instantaneous value of power. So this current multiplied with voltage on the positive peak will give you the value of power in this fashion. Okay, now negative voltage with negative current, negative negative gives the positive power. So in fact I'm going to get the power in this fashion. So in fact this becomes a sine wave to unidirectional wave. This is called as sine wave, whereas this becomes a unidirectional wave because the outputs of power are obtained in one direction. So it becomes unidirectional. So this is how we need to understand mathematically and technically the behavior of sine wave applied to resistor. In my later classes, I am going to give the waveform related to inductor as well as capacitor, how they are going to behave when voltage or current is made to pass through them. So this is what we are going to see in our later classes. It's a very short class, but it is going to give you the importance behavior of a sinusoidal input applied to a resistive load. So hence, this is how the power output obtained for pure resistor under the behavior of sinusoidal input. So if you like this video, please share among your friends and subscribe to my channel. This is a very important factor. Please subscribe to my channel and please like as many likes you can uh, give to this particular video. This will give a boost for me to go with the latest videos. And please press the bell icon for the future notifications. Thank you.